So first, let me introduce myself. My name is Taddasa. I'm from Ethiopian Institute of Agricultural Research. I'm a senior ICT expert, and currently I'm working on UAV and other technologies for research, mainly focusing on ICT for agriculture and digital agriculture practices. So my presentation title will be on the application of unmanned aerial vehicles for high-throughput phenotyping of the wheat breeding trials in Ethiopia. So I will share our experience on the use of UAV for specifically for the research purpose, focusing on wheat breeding trials in Ethiopia. So here is my, sorry. Okay, here is the contents of my presentation. So first, I will briefly discuss about the digital agriculture or the ICT for agriculture initiatives in Ethiopia in general, in particular in our institutes, which is Ethiopian Institute of Agricultural Research. And then I will discuss mainly on the research results on the use of UAVs for high-throughput phenotyping in wheat breeding trials. So, and I'll also discuss on what the challenges we face during this practicing drone for the research purpose and the limitations, and also our future plan. Digital agriculture, there are many initiatives in Ethiopia by different organizations on the use of digital technologies for agriculture, for both research and also for the development. So like other African countries, agriculture plays a significant role in Ethiopian economy. Actually, this figure might not be exact, but more than 70% of the employment is mainly on agriculture. So like other African countries, agriculture plays a significant role in Ethiopia. So when we come to the digital agriculture perspectives or initiatives in Ethiopia, we already have a digital Ethiopia strategy on that. Agriculture is one of the main pillars, and there is a national ICT policy. At the same time, ICT for agriculture strategy there is one pillar on that, and the digital green project, the 8028 hotlines, and the e-voucher systems, the livestock management systems. All these initiatives are, currently undergoing by different government organizations, development, international organizations, and private sectors are also recently engaging in these digital agriculture practices, from across the value chain, especially on the area of extension. So among this application of drones in agriculture is also promising. Unlike other African countries, recently we started using drone for research and other practices. So I'll focus on that and I'll make presentation. When we see some of the digital agriculture initiatives, there is a soil information system and remote sensing, and also there is recently one advisory system, which is the Ethiopian Digital Agriculture and Extension Advisory Services. There is already in place. This is actually a roadmap which is developed by the Agricultural Transformation Institute and the Ministry of Agriculture. And as I mentioned earlier in my slide, there are many tools, platforms for reaching the farmers. And very recently, the Ethiopian government already in place the strategy on digital agriculture roadmap, which is launched by the Ministry of Agriculture, ATI, and other partners. Our institute also part of this roadmap. So this is really a big achievement for on the digital agriculture. So this is some of the initiatives by the Ethiopia. And when you come to our institute, Ethiopian Institute of Agricultural Research, it is a government organization which conducts research at its different federal research centers. We have more than 20 research centers all over Ethiopia. So in our institutes, we have the ICT department, which is responsible for delivering ICT services, focusing on developing different platforms and providing the network and other infrastructures for research purpose. And also the department which I belong is Climate and Computational Science Research Directorate, which is mainly working on climate, geospatial, GIS, biometrics, and digital agriculture. So my presentation will focus on the digital agriculture aspects, which is being implemented in this directorate. So yeah, this is actually to show that EIAR, the Ethiopian Institute of Agricultural Research, is, it's a reservoir for immeasurable knowledge. So there's the big knowledge hub, as you can see on the map. There are more than 23 research centers all over Ethiopia. So these all research centers generate huge data. So actually there are also other federal regional research institutes, and at the same time higher learning institutions or universities are also working on this. So there is a huge data on this. So when we see some of the ICT for agriculture efforts in our institutes, on the data collection, management, and interpretation aspects, there are initiatives using different digital devices for collecting data and data interpretation. Also, we are using different platform softwares for that. And also there is a knowledge hub or the knowledge management system where we archive research outputs. So these are accessible by external users and also our researchers. And then our aim is to generate an advisory mainly from this big knowledge. And so we are working on that. So I think there are some already initiatives on that. These are some of the knowledge bank or the platforms that we are using for that. For example, crop protection package, the natural resource package, the livestock package. So all these are accessible for the researchers and external users. And at the same time, we are generating advisories from this, which can be reached to our farmers. So this is a huge development. So, but the problem is, still our platforms are not integrated with each other. So this is what now we are working to integrate the different platforms so that the different knowledge can be generated from this. Actually, our institute is not mandated to reach farmers, but we are reaching farmers through the Ministry of Agriculture and other private actors who have already deployed their own platform to reach the farmers. Actually, the AT28 outline farmer, which is managed by the Ethiopian Agricultural Transformation Institutes, have more than 5 million registered farmers. So with this platform, it will be possible to generate an advisory and reach farmers and also get back the requests from the farmers. So actually, some of the major achievements or platforms that we are using and which can be a good lesson for other African countries is the Ethiopian Wheat Early Warning System, which I'm part of the project and I'm managing the system. So I don't want to go in detail, but in the system, we are working on the rapid detection of the disease, which is really a devastating disease. Maybe, I don't know, in Kenya and other African countries also, they are, having challenging on this disease. So there's a forecasting model, and then finally advisory will be generated, and farmers will get this advisory through different channels, mobile applications and web platforms and web through the text and voice-based services. So this is one good initiatives and a very good experience for the other countries. And the other one is we are using drone for agriculture in Ethiopia. Actually here, Ministry of Agriculture, our institute, ATI, and other private sectors also now already started using drone for different purposes, like both the mapping drones and the spraying drones. For example, drones are now being used for locust monitoring by the Ministry of Agriculture. And in our institutes, we are using drone for research purpose. And in ATI and other organizations, they are trying to use drone for yield estimation, both by integrating AI with drone. And also some private sectors are now providing spraying drone services. So the picture you're seeing on the right side is when we provide training for Libyan and Ethiopian experts on the use of drone for spraying drone technology. So these are the initiatives. So specifically in this presentation, I'll focus on the use of UAVs for conducted in 2020. So yeah, actually plant phenotyping, it refers to the quantitative or description or measurements and assessments. So which is really very important for research. So our researchers, they have thousands of plots, and from those thousands of plots, they collect different traits. But the big problem is this currently our researchers are using a conventional method to collect data. That means they just visually score the data, and mostly they use a manual measurement method, which is very time consuming and susceptible to human error, and also highly labor intensive. So I have personally visited the different experimental fields when the researchers collected these traits. So it's really highly biased, and also the measurement is more depends on the visual. So, and also quantitative analysis of some plot level metrics and extracting agronomically important phenotypic traits is challenging, especially in large breeding trials. When you have thousands of plots, it's really unmanageable. So due to this, many important traits are not still collected or difficult to collect. So as you can see here, this is a conventional phenotyping tools, which is very slow, costly, technically challenging. Actually, I took this slide from the presentation by CMIT. So as you can see, either the breeders or the pathologists, they collect data on the field at the same time in the laboratory manually, so which is really difficult. So to address these challenges, now remote sensing platforms like the UAVs are recently being tested and used for various phenotyping of breeding trials. Many research are being conducted now to use drone and satellites imagery for high throughput phenotyping. So as you can see here, it will be possible to do the phenotyping across different spatial scale. So at leaf level, also possible to use some mobile applications and get the phenotyping. And also there are many ground-based devices where we deploy and collect the data. So already the different researchers already confirmed that high throughput phenotyping using drone performs better than satellite and some proximal sensing devices, because one, it will be possible. It's very easy to fly drone and collect data at any time, and at the same time, we can, spatially, we can collect data at different scale or resolution. So that's a very big advantage. So currently, the drone technologies are now advanced, and it's possible to use the drone for this purpose. Yeah, the recent development on data collection management also give the advantage for using drone for this purpose. So in general, this is the non-invasive approach, and which reduces error in data collection and accelerates the breeding process and research. So in developed countries, they are deploying this drone, and then they are accelerating the breeding process, which is really very important in releasing the varieties, which is the core in agriculture. So yeah, this is how this digital phenotyping or the remote sensing based phenotyping has advantage, which is non-invasive, very fast, and multiple spatial temporal dimension, and it can potentially be cost effective. So when you come to in Ethiopia, so actually I already mentioned some of the problem statement. So still in our institutes, very limited traits are collected, and conventional methods are used for evaluation and measurements, and data collection is costly, and it's difficult to get some new insights. So it's because we are using conventional method. As you can see on the picture, one of our researchers. He is just collecting different data. Actually, they are using a mobile app, but still using the mobile app, they are visually scoring the different data. So that's really very challenging. There's a back pain and highly biased. And at the same time, as you can see at the right corner, at the lower, the bottom, thousands of plots are there. This is one drone aerial view, which we took at one of our research centers. So really unmanned aerial vehicles can play a great role. So when we see actually the phenotyping in our institute, still the current status is, we can say is just somehow better. So still we are not using the cutting edge technologies like advanced technologies for phenotyping. We are heading to that one, but still we are transitioning from the basic manual-based data collection to this cutting edge technology. We are in transition to this one. So this is just so the mainly the objective of our research was to evaluate how drones can be used for disease scoring and severity analysis in weeds. And then the other objective is to design and develop a model for automatic detection of weeds yellow rust, because other rusts are really difficult to detect. So we are focusing on the yellow rust to detect, and for that we are trying to use different machine learning and even deep learning techniques. And then our aim is finally to produce a high sort of digital imaging and analyzing pipeline, which can be integrated on the current, breeding pipeline. Already there is a breeding pipeline, but this remote sensing based pipeline needs to be integrated in that process. So that is our aim. So based on that, so actually this is how we created awareness on the use of drone. Actually, we already discussed or awared our researchers and how drones can be used for agricultural research, for collecting different data. And at the same time, even for farmers, we demonstrated drone and how drones can benefit the smaller farmers by collecting different data, monitoring their crop, and getting insights on the crop health data and other things. So actually, we had a very good experience, acquiring images from the farmers field, from the research, and even from some research centers also for mapping. So this is the study sites which I conducted with my colleagues. It's located in the southern southwest part of Ethiopia. It's called Bakoji, and the purpose is to select the highly yield disease resistance. So the number of plots in total are almost 1,000. So this plot size, the different varieties, and also diseases are actually with natural disease infestation. So no chemical was applied. So actually that area was highly susceptible for both yellow rust and stem rust. So that's why we choose that specific location for our research. So this is the experimental field layout and the plot number. As you can see, actually it has some 4 blocks, and for each blocks we have different number of plots. So in our research, we focus on the first block, which contains 116 plots, which is 10 by 16 rows and columns, mainly because to avoid interference with other blocks. And at the same time, that block was somehow, it has a diversified number of varieties. So we choose that block in our research. So what we did was we flew our drone and collect imageries, and actually at the ground also our researchers collected the ground data. I will show you the detail of the type of data they collected. So data like days to heading, the disease related data, the plant height. All these are collected by our researchers at the ground. And at the same time, we use our drone and acquire imagery on these dates. Actually, the dates were not exactly overlapped due to different difficulties. We could not acquire the image at the same or 1 or 2 days difference from the ground scoring. That is the one challenge. So as I mentioned, this is the data and the traits collected by our researchers. Data like days to heading, days to maturity, plant height, all these are collected. Even the grain yield after the harvest also collected. So we got all this data. And also actually this is how the scoring was done. The researchers, they took some 5 pointers in each plot, and they score the disease incidence and the disease severity, which is biased, and it depends on the researchers. Highly experienced researchers might score very good, but someone who is who is not unexperienced might score differently. So this is the biggest challenge in scoring. So our research aim is to address this challenge and use drone imageries and automatically generate scoring for plots by calibrating. So this is just to show how this scoring was done by the researchers. So actually, these are the image we acquired. Actually, there's 5 rounds in August, September, October, and November. So actually, we collected more than 5,000 images. So actually, mainly our flight altitude was from 20 meters to 30 meters. So the resolution is almost from 2.2 to 2.9 centimeter per pixel. That is the density. So actually, we use the standard overlap, which is 80 by 70 meters. So this is the drone we used during the data acquisition. Actually, it's called the Parrot Bluegrass drone, which is designed for agriculture, but actually it has some advantage and disadvantage. I've seen many African countries, they have already got this type of drone, and they are using for monitoring purpose. So actually, we also use some open source and licensed software for data analysis. Mainly, we use a Pix4D mapper, which is really very nice in stitching images. And also, we also tried other softwares for that. So for phenotyping and mainly for segmenting the plots, we used the Plot Phoenix software, which is licensed, Solvi, and also which is licensed, and Field Image R, which is based on R, and which is an open source. So I tried to use these softwares for segmenting the image which is acquired from the UAV data. So this is the methodology we followed during our research. So UAV images were acquired, both the RGB and the multispectral image were acquired, and then we generated the orthomosaics from both, and different vegetation indices were generated, and actually plot level metrics, the vegetation indices generated. And at the same time, ground data was collected mainly on the crop at different crop growth stage, and yield related, and the disease and height, different type of traits were collected. And then so we tried to analyze the correlation between this ground data with image generated data. So that's how we tried to use, and also we tried to predict the yield from this data by correlating this ground and UAV imagery generated data. Actually, this is the standard image acquisition procedures we followed. So before each flight, we calibrate our drone so that we can get better precise imagery. So actually, we used also some ground control pointers for that, so that it will be possible to for during the stitching. So actually, these are just sample randomly selected RGB image for at different growth stage, which we took during in August, September, October, and November. So as you can see in the picture, during August, it was really at early stage, and as you can see, the greenness and the maturity was not that much. And then mainly in September, we can see a very good development, and plots are clearly visible. And then after that, it gets mature, and actually the disease development also difficult to observe. So mainly we focused on using the data we collected in September and October for our research purpose. Actually, this is how we generated the orthomosaics from the raw data we acquired for all plots. And then we used Plot Phoenix software, which is actually licensed, but I got some free trial for some 2 months to analyze my raw image data, and then I use this software. It's really very nice for generating plot matrix. So actually, you can upload your raw image data at the same time. You can also upload the orthomosaic image and generate plots level data, different matrix. So plots will be generated from the raw image, as you can see. And then actually, as you can see here, from that, automatically it will generate different color maps, like here, the raw length was generated, and then the raw length means, for example, as you can see here, the one which is circled in red shows 6.68, which is a very low raw length, which means that specific plot has some problem. Either there is a missing plant, or it might affected or by disease, or there is some problem. So with that, the researchers, he can use this color map, and automatically he can go to that specific field and check that specific plot, what the problem. So this is really very nice. So actually 6 rows are already there, so you can determine the number of rows in the software. For example, if you have 4 rows, you can set 4, you can make it 3, whatever you want. So that's really very nice, the software, which is really very nice for the research. So you can set the number of rows, and then from that you can analyze the raw lengths and other data, and get the different information. At the same time, not only raw lengths and other data also can be generated. So this is how the rows are generated, as you can see here. And at the same time, vegetation color map and different matrix can be generated, as you can see here. Sorry, it is a little bit distorted, but this is to mean this one. So this is a nice software. And I also used Solvi, which is really very nice in grading and segmenting the plots. So using the Solvi, you can just upload your raw image data and generate orthomosaic, and at the same time different vegetation indices can be generated, even different zonal statistics can be generated. So it's really very nice software, but it's a licensed software. So I use this software also to generate plot level data and compare the different plots. So in my research, I used these vegetation diseases, which are mainly related with disease, because my focus is on wheat yellow rust. So I generated the JNDVI, MSIV, and NDVI and other indices, more than 12 vegetation indices for each plot. And then from that, I just statistically generated, tried to see how these image generated vegetation indices are correlated with ground data. So as you can see here, my focus is how this UAV generated indices are correlated with grain yield data, plant height, and also this coefficient of infection is disease severity. So I found that mostly it's obvious that the disease is mainly highly correlated and actually negatively correlated with grain yield, and the different indices more those who are related with red near infrared are more correlated with the grain yield. So this is a correlation matrix which I generated, and at the same time, I try to generate some graphs and see how the different weights indices are correlated with the grain yield, as you can see here already, which I mentioned. So this is the coefficient of infection is negatively correlated with the grain yield, which is obvious. And among the weight indices, which are derived from the multispectral imagery, those who are based on red and reddish and near-infrared bands exhibit positive correlation with the grain yield. But the magnitude of this correlation is, very weak, actually below 0.5. But still, we can say that comparing to the RGB generated indices, the multispectral imagery generated are correlated with the grain yield. Actually, I'll discuss why this is really very weak. It's because of the ground data. So I also tried to use different machine learning models and predict yield at early stage from the different weight indices. So actually, the random forest it has achieved the lowest root mean square error values, and also it has better prediction capacity comparing to other machine learning methods, actually. But I need to check this one on different states. This is just only for the image we acquired in September. So I need to cross check and check how we can predict yield at early stage, maybe at early stage of the early growth stage. So this is the result. So when you come to the limitations, actually, the data quality was a big challenge. Actually, the resolution, alignment, overlapping, and also the experimental field was not specifically designed for our research purpose. That was another problem. In the software-related challenges, hardware processing also another challenge. A computational and storage requirement, and the flight time was not on demand. So, and as you can see in this also, some of the image we acquired was, there was a wind, so it was not, the rows were not clearly visible. So that was a challenge. So actually, in general, when you come to on the application of drones in agricultural practices, there are challenges related to cost. Actually, we got these drones by donation, and buying drone by farmers, by researchers, really it's very expensive, and regulation is another issue. Like some other African countries, still the regulation is not fully in place. Actually, it's at the draft stage. So this is another challenge where we are not fully able to implement the technology. So UAV technologies are moving ahead faster than the regulations. It's similar to other African countries due to the security and other reasons. So regulation is still challenging, and lack of awareness is another challenge. Actually, drones are now very famous in Ethiopia, but not in agriculture and other sectors, mainly for military purpose. Many people, they know how drones are, being used. So the lack of training is another challenge. Actually, we are trying to provide training for agricultural experts, even farmers, and also even within 2 weeks' time, we have a plan to provide training on the use of spraying drone for smallholder farmers. So still, there is a lack of training and awareness, but there are some initiatives. So these are the challenges, and also at the same time opportunities in Ethiopia. So in conclusion, we already tried to apply drone or introduce UAVs for research purpose. And in our study, we found that the UAV technologies are efficient for data collection and monitoring of wheat trials in breeding programs. So we advise crop breeders, scientists to give more attention for such technologies which accelerate the breeding process. So our aim is, as I mentioned in my introduction, our aim is to prepare a breeding, drone-based pipeline and integrate that into the existing breeding program in our research institute, and beyond that to other research institutes in Ethiopia. So yeah, our next plan is to design and develop a model for automatic detection of wheat yellow rust disease, as you can see at plot level from aerial image, mainly plot level disease detection and quantification. That means scoring the data. So automatically from the UAV image, and even in the future from the image captured by the mobile app, the researchers will be able to score and detect the disease at plot level. So this is what we are planning to do in the future, in the near future. Yeah, actually, apart from my research, I did also some research in collaboration with CMIT, which is an international organization. So we used our UAVs, and they acquired some high resolution satellite imagery, and we tried to see how disease can be detected and also can be used for high-throughput phenotyping. So this experimental field trial was specifically designed for our drone purpose. So already our work is published on the Nature scientific report. So as you can see here, you can access that one, and you can refer our research. So this is one of the results, which is already published results. So this is it. I think I'm not sure whether I'm finished in time. If there's some question.